Next is Johnson's rule for scheduling. Johnson's rule for scheduling. This we use if there are n machines and n jobs. Earlier we have done sequencing methods where there is on one machine if we have different processing times of different jobs. So then which is the first method? I mean like first come first serve. That is for one machine. There are n machines. So for each job you need to schedule on which machine it has to process first, and even based on that you have to get the sequence. This is actually done by using Johnson's algorithm. So first we start with two Johnson's method, two machines and n jobs. So that means n jobs will come on two machines. Step 1. Select the least processing time. If the least processing time, suppose we have, for example, in two machines and n jobs, we have n into 2 cross matrix. We have 2n processing times. Out of the 2n processing times, whichever is minimum, select least processing time. So if the least processing time is in machine 1, then the job is scheduled as early as possible. And otherwise, if the least processing time is in machine 2, then the job is scheduled as late as possible. If the least processing time is in M1, then schedule the job as early as possible. If the least processing time is in M2, then schedule the job as late as possible. So the sequence of jobs goes from machine 1 to machine 2. So every job has to first go through machine 1. Once the complete operation that processing operation is over on machine 1, then only it will be sent on to machine 2. So once it operation on machine 2 is over, then it will be taken out. So this is the scenario. So this in step 1 we just look at the processing time all in machine A and machine B combined. Whichever is minimum we take that machine processing time, and we look that if the processing time is belongs to machine 1, then we give that as a job, we schedule that job as early as possible. If that processing time is in machine B or machine 2, then we schedule that as late as possible. Step 2. Select the next least possible time. Select the next least possible time and repeat the above step till all all our machines jobs will get allocated, and repeat step 1 till all jobs will get allocated. Step 3. Calculate the make span time and idle time of each machine. So we start with one simple example. So processing time of the problem here, he has given 5 jobs and 2 machines. So processing time of 5 jobs on 2 machines are given in table. Determine make span time using Johnson's algorithm. So the job, he has given 5 jobs A, B, C, D and E. So on machine 1 the processing times are given as 2, 3, 7, 9, 6. On machine 2 the processing times are 10, 8, 5, 1, 4. So all the processing times are in minutes. So to calculate optimum sequence, first find the least possible time. So if you look at the table, the least number you are finding is 1. the one value corresponding to machine 2 of job D. So job D of machine 2 has least processing time. So as per our discussion in the above procedure, the least possible time is in machine 2, which is to be machined last. So this D job has to be processed last. Then look at the next possible least time. So as the least processing time is on machine 2, so the job D is processed last. Similarly, next take another as a second step, another least possible time. Select second least possible processing time. So after removing the 1, what is the next least possible time? It is 2 is there. So 2 is the least possible time for next processing time available after removing 1. So then job A on machine 1 has to be processed first. So job A has to be processed first. So the optimal sequence modified after second step is A and last one is D. Similarly, look at the again look at least possible processing time available. So what is the value of the available least processing time after 1 and earlier we had 1 and then 2 was there, next is 3. That 3 is the next least processing time. So that 3 is on machine 1, so it has to be processed first. Okay. So the optimal sequence looks like after third step. So A, B and D. So again select least possible processing time in remaining. So if you look at the data, you will see another least possible time in the remaining values is 1 is over, 2 is over, 3 is over. Now minimum is 4. So 4 is on machine 2. 4 is the next least processing time. 4 is on M2, so it has to be processed last. So the sequence now looks like A, B. So D already we have given last. Similarly E. E is the last. So again look at the A, B, C, D. Only 5, right? Sorry. Only 5. So remaining is only C. A, B, C, E, D is the sequence. So optimal sequence after completion of this optimal sequence is A, B, C, E, D. So if you want to calculate the make span time, so first you need to write the optimal sequence B, C, E, D. So after writing that, write the processing time on machine 1 and machine 2. So machine 1 it is 2, machine 2 it is 10. Machine 1 it is 3, machine 2 it is 8. Machine 1 it is 7, machine 2 it is 5. Similarly 6 and 4, 9 and 1. So this is the processing time. So what is the time of in machine 1? That you need to calculate. So what is the input time and out time of machine 1? So if you look at the machine 1 processing time, so the value here it starts with 0 because that is machine 1 is the first beginning one. At beginning the processing time is considered as the beginning point is 0. So from 0 to how many hours it will process on machine 1? 2 hours. So the component will come out after 2 hours. That means 2 hours. Again, after 2 hours, the machine one is free. So once the job A goes out, job B comes into machine one. So how much time? 3 hours job B will spend on machine one. So 2 plus 3, 5. So after completion of the machine B, after 5 hours, machine B will go out of the, sorry, job B will go out of machine A 1. So then machine job C will enter into the machine 1. The processing time, minimum processing time required for machine C on machine, sorry, job C on machine 1 is 7 hours. 5 plus 7, 12. So by the end of the 12 hours, these ABC jobs will be over on machine 1. So for E will enter after 12 hours. E will process for 6 hours. So by the end of the 18 hours, 4 jobs will be processed. So again it will enter, the D job will enter at 18th hour and leave at 27th hour. So total it needs, so after 27 hours all jobs will be processed on machine 1. So once that is completed, then we have to schedule machine 2. Machine 2, as per our initial statement that machine job will enter into the machine 2 only if it completes the processing on machine 1. Without processing on machine 1, job will not enter here. This is our assumption. So once the job A after completion after 2 hours, it will be processed on machine 1, then move to machine 2. So in machine 2 from 2 to 12, because it takes 10 hours in processing time on machine 2. So 2 to 12 is after 12 hours the component A will be over. So after 12 hours, the component A, the job A, will be processed on machine 1 and machine 2. So that is done. So after 12 hours, machine B will enter. If you look at the output time of machine job B on machine 1, it is 5 hours. Even though came out of the machine 1 on after 5 hours, but it has to wait for 7 hours to get into the machine B, machine 2, because there is already job A is processing. It needs 10 hours. Similarly, for job C, even though if you look at the job C delivery time or output time of the machine 1, it is 12 hours, but when even after coming out, after completion of job machine 1, the machine 2 is busy. So machine 2 was free by 20 hours. By the time job C on machine 1 was waiting. So the job C will enter into the machine 2 at the 20th hour. So the processing time of job C on machine 2 is 5 hours So 20 plus 5, 25. So again, after 25 hours, job C will be also processed along with A and B. So after 25 hours, job E will enter into the machine 2. So here E processing is 4 hours. So again, after 29 hours, job D will enter. So job D processing time on machine B is 1 hour. So make span time, total time it took for the entire operations jobs on these two machines is 30 hours. So make span time is equal to the total time spent for entire completion of all operations of all jobs equal to 30 hours. If you look at the idle time of machine 1 is 0. So machine 1 won't be ideal. Only next machines will be ideal because machine 1 as a component comes in, it goes processing, and again once the component is processed and delivered, so a second component will enter into the machine 1. So components will be waiting for it. But if you look at compare with the machine 2, because once the component from machine A is completed, then only it can go to machine 2. If the a part a job in machine 1 is taking long time, then the machine 2 will be ideal here. So if you reduce this idle time in supply chain, then it will be more economical and efficient. So here in this problem, idle time for machine 2 is idle time for machine 2 equal to 2 hours. How we got 2 hours? If you look at the machine 2 started at after 2 hours of machine 1. So that means machine 2 was ideal till machine 1 sends one job at least out. So once the machine 2 started, it didn't took any break till the end. It was continuously running. So here the ideal time of machine 2 is the 2 hours which happened at initial stage. So remaining all other so total max span time of this system is 30 hours, and these are the important, and one is on after selecting the sequence, then you have to decide the factors based on the business perspective to select what to like to send to select the which sequence makes sense, and what is total makes time required to complete the entire operations on each these methods.